Alright, today folks we are going to be looking at exponentials and logarithms. We're going to be learning how to convert an exponential form to log form and vice versa. Okay, so let's begin by looking at our first problem right here. We've got 3 to the 5th equals 243. Okay. Well, looking at this right here, this is an exponential form because obviously right here that 5 is your exponent. Okay. All right. And remember that the number or letter, the term that's being raised to the exponent, is called the base. So here 3 is your base. And then finally right here I'm going to call this your constant. Now although I'm calling it a constant, sometimes we get a little confused and think constant is always a positive whole number. But a constant is simply a number without a variable. So here we see we have a number without a variable. So our constant here is 243. It could also be a fraction. Sometimes we get a fraction right here, and that's perfectly fine. Okay, so what we have here is your exponential form. All right, and think about the root of exponential. The root of exponential, the root word, is exponent. Okay. When you have a form that has an exponent, it is an exponential form for our unit here. So this is in the form of your base raised to your exponent is equal to our constant. And we're going to take this form right here and change it to log form. Now, I know you're thinking, well, why do you have to change it to log form? All right, the reason why, if I gave you something like 3 to the x equals 9, you could easily look at that and say, oh, well, x is 2 because 3 squared is 9. But if I gave you something like 3 to the x equals 15, well, 15 cannot we cannot get a result of 15 by saying 3 raised to a whole number. 3 to the first is not 15, 3 squared is not 15, 3 to the third is not 15, and so forth and so on. So by converting this to logs, it allows us to use the algorithm behind the logs to find what that x should be. So we're going to convert this to a log. All right. So to convert it to a log, you literally write the word log. Then as a subscript, you're going to put your base. Then we've got our constant. It's equal to our exponent. Okay, so again, the base is your subscript. And remember, a subscript is simply a term below your normal line. So the way that we read this is log base of your constant equals the exponent. Okay, so if you're changing it from an exponential form to a log form, we're going to simply say the log of our base, so the base would go right here, your constant value goes right here, and your exponent goes right here. So I'll give you a chance to copy that down. And one way that I always remember this, if you think about it, the base going on the bottom. All right, if you have like a basement's at the bottom of the house. The base of a cheerleading pyramid, if you are a base in a cheerleading team, on a cheerleading team, you are the bottom of the pyramid. You are the support of the pyramid. So the base is on the bottom. All right, so let's convert this right here. We're going to change it to log form. Okay. And how are we going to know it's in log form? It literally has the word log in it. Okay, so we're going to say the log. All right. Our base is 3, so right here we're going to put a 3. Our constant is 243. and then our exponent is 5. So we're going to say log base 3 of 243 equals 5. That's how you read it. Log base 3 of 243 is 5. Alright, so as you can see right here, I've got a little U-try. So let's take about 1 minute. I want everybody to try that U-try problem. Convert this exponential form to a log. Alright, so let's see how you did. Again, you're going to try to always remember that you literally have the word log there. Okay, so what is our base? Alright, our base right here is a 4 because the 4 is being raised to the exponent. So we got log base 4. What is your constant? Your constant here is 218. And then what is our exponent? Our exponent here is x. So we got log base 4 of 218 equals x. Alright, now before we move on, I want to show you something how to evaluate this in Desmos real quick. Okay, so notice that we know all of our values for the log portion here. Okay, so in Desmos, what you're going to do, let me open my phone up to Desmos real quick. All right, let me turn the light off so I won't have a glare. So give me just a second. All right. So we're going to come right here to functions. Okay, so the first thing we tap is functions in Desmos. All right, we're going to scroll down to the calculus menu. All right, now notice right here in the calculus menu we've got 2 choices for a log. All right, so your 2 choices. You're going to choose a log if you don't see a base. Now really, it's a base of 10. So it's common base 10. And you're going to choose the log base A if you see a base. So you have a base. Now again, probably not using the right terminology here, because when you don't see a base, there is an understood base of 10. Okay, but most of the time students always say, oh, there's no base, so we just kind of go with that saying. If you actually have a base, you're going to use the log base A. So that's what we're going to choose here. So I'm going to choose log base A because on this problem I do have a base. So I'm going to do, notice right here it sets it up just like it looks. So I'm going to do a base of 4 and a constant of 218. And that's going to give me my value for the log base 4 of 218. And that's how you use Desmos to evaluate your logarithms. Okay. So this is telling us that 4 raised to the 3.88 is going to equal to 218. Now obviously, if I come right here and say 4 raised to the 2.88, oh, I put a 2, I meant 3. I was like, something doesn't look right there. Okay, it's supposed to be 218, but since we rounded right here, we're just a little off. But we're close enough to know that we're right because 216.76 is close to 217, so we're only 1 off from 218. And if I didn't round, if I used the entire decimal, I would have got 218. All right, so if you'll pause the video, let's take about maybe 4 minutes and try the classwork problems right here. So pause the video for me. All right, so let's see how we did here. All right, for number 1, we've got the log, our base is 4, our constant is the fraction, 1 over 256, equals our exponent of -4. For number 2, we've got the log, our base is 2, constant is 32, and then our exponent is 5. For number 3, we've got the log, base 196 of 14 equals our exponent of 1/2. For number 4, we've got the log, base 64 of 4 equals 1/3. For number 5, you should have got log base 4 of 256 equals 4. And finally, for your last classwork problem here, the log base 4 of 1024 equals 5. Now, one way you could always check to see if you've converted these correctly, you can use Desmos to verify your answer. So right here, if I go to line 1, to the left, so if this is correct, the left side should equal the right side. So I'm going to go right here to line 1, go to functions, scroll down to calculus. I have a base, so I'm going to do log base A, 64, 4, I get 0.33, and then my right side, if I do 1 divided by 3, I get 0.33. So the left side equals the right side, so that tells me that I converted these correctly. All right, so we converted exponentials to logs, so now let's look at converting logs back to exponentials. Okay, so we're just going to do the reverse process. Okay, so remember, in exponential form, you got your base, your exponent is equal to the constant. So right here, in A, my base is 7. So I'm going to have 7. My constant is 10. And my exponent is x. So I got 7 to the x equals 10. All right, for B, all right, my base is x. My constant is 7. My constant is 14. My exponent is 7, so x to the 7th equals my constant of 14. And until you get used to it, you could come right here and put log base constant equals exponent. So my base was x, my constant was 14, and my exponent was 7. So pause the video right here. Let's take about 3 minutes to convert these right here. All right, so let's see how you did. All right, remember your base is always your subscript. So right here I've got a base of 3. My exponent is -2, and I get 1/9. Right here, number 2, my base is 8. My exponent is 1/3, and my constant is 2. For number 3, I got a base of 81. My exponent is 1/4, and my constant is 3. And if you want to see if these were correct, you could go to Desmos and put 81 raised to the 1/4, and it should give you an output of 3. All right, now for number 4, notice we don't have an equal to right here. Whenever you don't have an equal to, it's an understood equals x. So again, whenever you don't have something equal, then it's an understood equals x. So here we're going to have 3 raised to the x equals 1 over 243. For number 5, we're going to have 5 to the second equals 25. And then for number 6, we're going to have 7 to the negative 3 equals 1 over 343. So conversions are pretty easy. It's just remembering where each part lays. Where's the base? Where's the constant? Where's the exponent? Okay, and that's all there is to conversions. Pretty simple. The next thing that we're going to look at are properties. All right, so these are kind of like the rules that go along with your exponentials and your logs. Okay. All right, some of these properties have names, some of these properties do not have names. It does not matter which ones have names or does not have names. That doesn't make one more important than the other. Okay. So let's look at this first one. Okay. So for this first one, I left a little bit out because I wanted to be able to write this in color instead of having it typed in. Okay, so right here, our first property, if you have log base A of A raised to the n. This is actually a typo. Instead of a 1, it should have an n right there. So write that as an n. I just noticed that. All right, the rule says if your base and your constant are the same, then your answer is actually going to be your exponent. So what does that mean? If we had the log base 7 of 7 to the 9th, we want to evaluate that without even having to use the calculator. See how your base and constant are the same? Whenever your base and constant are the same for a log, it's going to be your answer is going to be equal to the exponent of your constant. So here the answer would be 9. And just to prove it to you, all right, if I come right here, log base A, 7 raised to the 9th, and look at there, our output is 9. If we had the log base 4 of 4, what is our answer? All right, well notice I don't see an exponent, but when I don't see an exponent, I know it's an understood 1. So since the base and the constant are the same, it's going to be equal to whatever the exponent is of my constant. So that's going to be a 1. All right, moving along to our product property. Now the product property and the quotient property are probably some of the most used ones, and also adding 1 or 2 more on the next side. But our product property, notice here we got log base B of x times y. All right, this is a single log. And I'm trying not to sing all the single logs. All the single logs. Okay. All right, so think back to 8th grade math and probably a little bit of math 1 when you learned the rules for exponents. You learned that when you are multiplying like bases, you add the exponents. So that rule right here kind of applies to logs. When you are multiplying, you're going to add the logs to put it in expanded form. So we want to go from single logs to expanded form. So what we're going to do, we're going to say the log base B of x, since x was given to us first, plus log base B of y, since y was given to us second. So to take it from multiplication, from a single log to an expanded form, you put addition in the middle. And they both have the same log. So this is expanded form. All right, quotient property. Okay, so quotient means the answer you get when you divide. Product means the answer you get when you multiply. So here you notice we got log base b of x divided by y. Well, the exponential rules say that when you divide like bases, you subtract the exponents. So if we're going to go from all the single logs to expanded form for this one, we're going to use subtraction. So if you're dividing, you're going to subtract. So we're going to come right here, we're going to say the log base b of x, since that's in your numerator, minus the log base b of y. And that's how you change it from single log to expanded log, or excuse me, expanded form. All right. Move into our next side. All right, the power rule. All right, so this is also a rule that we're probably going to use a lot. Okay. The power rule is pretty easy. It simply says if you've got the log base b of x, and x has an exponent, you move it to the front. So this is going to become a times the log base b of x. So for example, if we had the log base 7 of x cubed, we're going to take that 3 and we're going to move it to the front. So we got the log base 7x. We take that 3 and we move it to the front. So that becomes 3 times the log base 7 of x. All right. Your one-to-one rule. Okay. All right, so your one-to-one rule says if you got a log base a of x is equal to a log base a of y. You got a single log on the left side of the equal marks, and you got a single log on the right side of the equal marks. As long as the bases are the same, they're going to cancel the logs out, and you're left with x equals y. So for example, if I had the log base 7 of x plus 1 equals the log base 7 of 5. I got a single log over here, and I've got a single log over here. Nothing else is attached. You might be thinking, well, what about this x plus 1? Well, this x plus 1 is inside parentheses. That makes that one term. So the log base 7's cancel. And I'm left with x plus 1 equals 5. So that becomes a solvable equation. Opposite of adding 1 is subtracting 1. These cancel and I get x equals 4. Now, the inverse rule, which I call the big base rule. Okay, the big base rule is also another property that we use a lot in solving logs. Okay. All right, so the big base rule says that if you have a base with the log as your exponent, and that log has a base that's the same as your big base, then they're going to cancel, and you're left with just n. Now, what in the world does that mean? Well, let's look at an example. So if I had like 5 raised to the log base 5 of 2. All right. See how the big base and the little base are the same? So that cancels, and we're left with just the 2. So 2 is your answer. And just to prove it to you, I'm going to go to my Desmos. All right, I'm going to put this right here. All right, so 5 raised to the exponent. Now we got to put parentheses around this. All right, go to functions. Log base 5 of 2. And look at there. Alright, now this property right here, I've seen maybe once used, so it's not that significant, but it's still a property. Alright, this says if you have the log base b, so the base can be anything, and if your constant is 1, it's going to always equal 0. Alright, so let's just choose a 7 and put a 1 right there. We get a 0. If I change that 7 to a 15, it's still 0. So if your constant is a 1, it does not matter what your exponent, your base is, your output is always going to be a 0. Now, the change of base formula used to be a really important property, but now that we've got Desmos and some updated graphing calculators, we don't use the change of base as much. But it used to be that you couldn't have the function right here. That the calculators did not give you the format for the logs. So you had to manipulate the calculator so that you could actually find the output. So what you would have to do, you would say the log of your constant over the log of your base, because the base would always go on the bottom. So like right here, see I got log base 15 of 1. I would actually have to come in here and say the log, I forgot, I've got to update it so it's not going to let me do it. Let's see if I can come in here and type in log. Log of 15 over the log of 1. Alright, and it gives us undefined because what that's doing is putting 0 in the denominator, so that's why it's giving us an undefined. Oops, actually, nope, I got it backwards, don't I? That's why. The base should go on the bottom. There we go. Now it makes sense. I was like, something isn't right. Alright, so let's look at some examples of how to apply these properties real quick. Okay. Alright, so right here, I see that I've got expanded form. Alright, so what they want us to do, they want to take it back to a single form. And I see I've got addition. So if we were adding, that means originally we had multiplication. So you keep the same base. So we got log base 6 of 3x times x. Well, we can actually multiply these. So 3x times x is 3x squared. So we get log base 6 of 3x squared. All right, for number 2. All right, this is a single log. So we want to take that from single and expand it. I see I've got log of 10 times x. 10 times x. So I'm multiplying, so I'm going to expand it through addition. So I've got log of 10 plus the log of x. Now notice this one did not have a base. When it doesn't have a base, it's an understood base of 10. So if you wanted to put a 10 there, you could, but you don't have to, because if it's not there, it's understood to be a common base of 10. So common base of 10. It's not a 1, it's not a 0. When nothing's there for the log's base, it's going to be a 10. Okay. Alright, for number 3. Alright, this is a single log. Okay, so it's got division, so we're going to come in here and we're going to subtract. So when we've got division, we're going to subtract. So we've got the log base 4 of x squared minus the log base 4 of 5. So I'll give you a chance to write that down. Whatever's in the numerator goes first. Whatever's in the denominator goes second. But if you notice, the x has a 2, so we've got to bring that 2 in front. So what we're going to end up with is 2 times the log base 4 of x minus the log base 4 of 5. I did not put the 2 in front of both logs because this was the only part that had the 2. The 5 did not have a 2. Alright, looking at number 4. Alright, so for number 4, I see I've got 2 operations going on, so we're going to do it from left to right. Okay, so we're going to take it from expanded form back to single form. So they all have log base 2, so I'm going to put log base 2. Alright, since there's addition right here, these two are going to be multiplied, so we got 5 times x. This is subtraction, so we're dividing by 3, so we're going to put all this over 3. That looked like it should be a lot more complicated than it was, but it wasn't. So again, here was addition, so I knew to multiply these two right here. And here this was subtraction, so I'm dividing by that 3. Alright, so we're going to omit examples 5 through 8, and we're going to come down here and look at how to calculate the values. Okay, so I've already shown you this on the front, but just as a little refresher. Notice this log does not have a base, so that's an understood base of 10. So when I choose my log, I'm just going right here and choose log and put 1,000. And we get 3. Alright, right here I see common 10, a base of 10, and a constant of 10, so I know it's going to also be 3 right here by just using my property on that one. Alright, here I've got no base as an understood base of 10, so I can just use the log. I'm just going to back this up right here and put a 15. Let's do 2 decimals, so to the nearest hundredths. So that 6 right there is going to make that 7 round up, so we get 1.18. And finally right here, log base 2 of 32. So this one has a base, so I'm going to go back into functions and choose the log with a base. Base 2 of 32. And we get 5. Alright, there we go. Alright, that's the end of our video. Make sure you put your name on your notes and submit them